Okay, welcome everybody, and back from the break. Is everybody having a great day so far? Yeah? Awesome. Okay. Well, I've got the great pleasure of introducing the next talk to you. So Paco is not only a colleague of mine at the Deloitte, but he's also a fellow Microsoft MVP. So Paco has been is a senior cloud solutions architect with over 18 years of professional experience architecting and implementing solutions, distributed applications. And more recently, he has a focus in Azure and cloud-based applications. So Paco is going to talk all about the good, bad, and the ugly of serverless today. So without further ado, Paco.
Thank you, Dan. Can you hear me okay? So first, thanks for being here. So you have 3 tracks to choose from, and you picked this one, so I'm very thankful for that. I'm also very thankful for being seeing the room full. So as Dan mentioned, I'm going to talk about serverless APIs, what's good, what's bad, and what's ugly about serverless APIs. So a bit about me. So I'm a Microsoft MVP, specialized in Azure. So you can follow me on Twitter. You can connect on LinkedIn as well. And the slides are already on SlideShare, so you can see the slides already are there. And so I have two code samples. They're already on my GitHub. Okay. So what we're going to cover today. First is what's serverless, what's all this hype about serverless, who are the main players in this space across the different cloud providers. Then we're going to discuss the different use cases that we can have with serverless APIs. Then we're going to go deeper into what's good, what's bad, and what's ugly about serverless APIs. Hopefully we have enough time to go through 2 demos. I prepared 2 demos for you, and then some key takeaways at the end, and we have some time, some Q&A. Otherwise you can find me in the event and just ask me if you have any questions if we don't have time here. So what is serverless? 2 months ago, I had the real pleasure of going to a cloud, one of the main cloud providers in Australia. They invited me to go to a data center, and I went to where serverless was hosted, and they allowed me to take one picture. So this is the picture I could take there. So as you can see, there are no servers, just empty racks. Right? So they are very smart, so this is how they implement serverless. Well, not really. Sorry to disappoint you, but there are servers behind serverless. So to tell you a bit more about serverless, so I prepared this figure where I show the different computing options you have on the cloud, and this is also to do with the different waves of evolution or innovation that has happened on the cloud. And you can see on the y-axis, at the top you have more control, and then on the x-axis you have at the right you have more productivity. So the first wave of cloud computing was IaaS, just virtual machines. So the same virtual machines you would have on VMware on-prem, you could have them now on the cloud, right? But you still need to manage the VMs, you need to patch the operating system and all that. So this would be the first wave. And then after that we had Faas, Platform as a Service. So Platform as a Service, now you start having load balancing and high availability. You would get 3 nines or 4 nines of availability, all managed for you. You don't need to manage, you don't need to patch the operating system and all that. So that was a great progress. And the last progress is serverless. So there's an additional layer of abstraction that we're going to discuss today. In this same spectrum, we have more options. So on the left to Platform as a Service, we have Containers as a Service, which some people call them serverless containers. So some people would say Containers as a Service are also serverless. We also have, on the left from that, we have Functions as a Service running on Kubernetes or container orchestrators. And then we also have low-code platforms who are serverless as well. However, because this is too broad, today we're just going to focus on serverless Functions as a Service, which is the most popular way of using serverless. Saying that means that we are not going to cover serverless containers like Fargate or ACI or Cloud Run. We're not going to talk about Functions as a Service running on Kubernetes like Knative or Kata or OpenFaaS. So these are topics by themselves. So we're going to focus just on Functions as a Service in a serverless way. So what is serverless now? Jokes aside, what is serverless and what are the benefits? So one of the benefits is that all the servers are abstracted. So there are servers, but these are fully abstracted. You don't need to worry about how many servers are running your functions. They are fully abstracted. You only care about the code that is running. And then the load balancing, the high availability is already built in for you. So if you have hundreds of instances, you only hit one endpoint, it's already load balanced for you. And high availability as well. If one instance goes down, the cloud provider would manage to put you another instance up, and then they will provide the SLA that they have agreed with you. And you might be thinking, well, I'm already getting this with Faas, right? So if I have an Azure web app, for example, I'm already getting this with Faas. So what's different from Faas to serverless? Well, there are two other characteristics. So the first one is they scale based on events, right? So if you have, for example, an app service on Azure, they scale based on CPU or memory, right? So if you have a burst of, let's say, 1,000 requests in 1 second, it will take 5 minutes to scale. So it doesn't scale that fast. In serverless, they scale very fast, and they scale based on events. So they are optimized to scale based on events. And the other big differentiator is that you don't pay whenever they are idle. So if your code is there but is not running, you don't pay for that. Whereas on Faas, you still need to pay for that instance, right? So these are the last two are the main differentiators between Faas and serverless. So all the cloud providers follow the same pattern, more or less. So the first is your code is being triggered by something. The simplest is a HTTP call, right? HTTP request, but also depending on the cloud provider, it could be a message on a queue, it could be a file drop somewhere, it could be something happening on a resource in your cloud provider. So depending on the cloud provider, you will have different triggers, and then that will initiate the execution of your code. Then you have your code, you have your business logic, and at the end you have outputs. This output can be, again, another file, or can be a message in a queue, can be sending an email, sending an SMS. Again, different providers would have different support for different protocols or services. But in a nutshell, all cloud providers follow the same pattern. So these are the main players. So the revolution started really with AWS Lambda. So there were some serverless offerings before, but the mainstream player started with AWS Lambda. And then later, Azure joined the party with Azure Functions, and then after that, Google Cloud Functions. And then each of them will have support to different languages or triggers. So in terms of languages, so the two most popular languages, the most popular ones are Python and Node.js. So these two are supported in the three of them. And then you see some .NET Core with C# and F# and PowerShell supported on AWS Lambda and Functions as well, or Go supported on Google Cloud and AWS Lambda, and so on and so forth. And regarding triggers, so all of them can be triggered by HTTP calls, but not only that. So depending, for example, an Alexa activity can call your AWS Lambda, or an event raised on event grid can trigger an Azure function, and so on. One message on a PubSub queue on Google Cloud can trigger your function as well, right? So depending on your cloud provider, you will have different triggers. And there are different use cases. So the most obvious one is where you have APIs, and these APIs can be called by a single page application, can be called by a mobile app, or a web app, or an IoT solution, right? So that's the obvious one. But we also have, for example, integration. So you can have applications dropping messages into a queue, right? And then your function triggers from that queue, do the translation, do the routing, do the enrichment, and then can deliver that message to the target application, can put that message into another queue. So these kind of scenarios of integration and PubSub services. We can also process data or events, right? So we can even process data in parallel with MapReduce or other approaches. We can also implement IT or Ops jobs or cron jobs. So we can say run this task every day or every night or every hour, or turn off this virtual machine at 7 p.m. every day, right? So you can schedule these tasks, and you can also implement backends for chatbots applications. So now that we understand more or less, at least high level, what serverless is, so now let's go deeper into the good, the bad, and the ugly of serverless. So what's good about serverless? The first one is speed to market. We're going to see in the demo. So you just focus on your code, everything is taken care of you. So instant management, scaling, even connecting to your service providers, the queues, connecting to the files, connecting to all those inputs and outputs is all managed for you. You focus on the business value, and this advantage is not only for developers, but also for ops. Hopefully we have time to see the tooling. If you have sporadic loads, then they are cost effective because you don't pay when they are idle. The scaling, again, as I mentioned, is event-based, so they allow you to support for bursty loads. All the tooling is evolving very fast, and they allow you to be very productive. And as I mentioned, the event triggers is not only HTTP triggers, you can trigger this by messages or files or all that. So these are all the good and all the benefits of serverless. Let's talk about what's not so good about serverless. The first one is vendor lock-in. Because you're using a programming model, so even though your code, you can export part of your code, the whole programming model and the whole advantage you get from one platform is very hard to migrate to another platform. And they would tell you, well, my runtime is portable. That's true, but then you're losing some of the benefits. So if you install the runtime locally, then you still need to manage that VM, right? So it is not serverless anymore. So it is portable. So many of these are portable, but then they end up not being serverless at the end. The programming models are opinionated, which means you can only do what the programming model allows you. So for example, this is just an example. Azure Functions, some months ago, like 6 months ago, you couldn't use dependency injection. So if you're a C# developer and you're used to use dependency injection, it was not supported. Now it is supported, but this is just an example. So there are other limitations. Again, if you are a .NET developer and you want to use the middleware clustering with your APIs, you cannot use that with serverless. So there are some limitations with the programming models. There are time limits. So depending on the cloud provider, there are limits. But for example, on AWS or Azure, you cannot run one single instance of function for more than 10 minutes. The technology is still maturing, so it's not something that I would recommend for every single scenario, and it's changing very fast. Sometimes I stop working with the technology for 2 months, and then after 2 months, my previous best practices are not best practices anymore, because now there is something new, something better. So this is a challenge as well for that. And the ugly of serverless, and probably you have heard of this, is cold starts. So what is cold starts anyway? So cold start means because you don't pay when your code is not being executed, your code is only stored in some kind of storage, right? So you have your code and they deploy the binaries of your source code in storage. So whenever they receive a call, let's say HTTP call, they have that listener always listening to listener always ready to receive requests, but the code is not ready. So when they receive a request, they need first to allocate a VM for you, and they're going to say, okay, this VM is going to be for you. After that, they need to install your code on that, deploy the code on that VM. And only after that, they will load that code into memory. And only after that, your code is going to run. So that means if your function is running idle for 20 minutes and you don't have any strategies for keeping them warm, then the first call might take 3, 5, 7 seconds, right? Depending on how heavy your code is. So that's a big disadvantage. However, if that instance is being called again, because that code is already in memory, then it's okay. So having cold start doesn't mean that every single request will suffer from this, but every time you're creating a new instance, you will suffer from this. And it's important to say that this only impacts if you're dealing with synchronous HTTP requests, right? You have a user waiting for a request, you have a SPA, user using a single page application calling a serverless, and then they need to wait 3-5 seconds, probably not so good, right? But if you're talking about integration between two systems, or like it can be HTTP or through a queue, it doesn't matter, right? So a system can wait 5 seconds, that's okay, or 3 seconds, that's okay. And there are some mitigation strategies. So you can, for example, schedule a job that is pinging or calling your function every 3 to 5 minutes, and then that will keep your function running all the time, right? And then you would minimize cold starts. This wouldn't avoid cold start at all, because you can, if you have 2 instances running, the one that is pinging is only pinging 1, right? So then whenever you need to scale up, the second instance will suffer from a cold start. Or the cloud providers, because they know this is serverless, they can just reboot your machine or recycle your machine and then give you a new one whenever they want, because it's serverless. So you're not meant to keep that instance up and running all the time. Okay, so having discussed all that, so we need to understand when it's not good to use serverless, even though we might have those use cases, but serverless is not always good. So the first one is if you have low latency and synchronous workloads, probably serverless is not the best for you. If you have constant load, let's say you have 100 requests per minute 24/7, if you're on serverless, it's going to be much more costly than having a PaaS solution that runs every time, like always on, right? Portability, if you need to migrate this to different cloud providers or running it on-prem, you could export the runtime, but again, you lose all the benefits. If you need full control of the infrastructure, again, you cannot do this because it's all abstracted. If your language is not supported, you need to use Rust or you need to use C, for example. Well, you cannot use serverless. Then again, if you need some of the features of your programming model, of your language, but the programming model doesn't support, then you cannot use serverless. Okay, so let's have some fun. So hopefully we can cover most of my demos. Okay, so the first demo is just a quick introduction to the programming model and the tools that we have. So this is a solution, very basic. So this is on C# and on Azure. So what it does is it's listening for a HTTP request, and then it receives that request. The body of that request, it's dropped into a queue. So that's the first function. And then we have another function that is listening to that queue, gets the message, and drop that into a document-based database, Cosmos DB or NoSQL database. So you would like to do that, for example, if you have order processing, you submit an order, and then the order processing might take 5 minutes because there's a lot of backend validation. You don't want the user to be waiting for 5 minutes, right? So you just drop the message into a queue, and then you have further processing. So I'm applying the same pattern here. And as can you read okay? Or shall I zoom in a bit? So this is the programming model of Azure Functions. And as you can see here, we have, this is the other one. This is the first one. So this is being triggered by a HTTP call and receives a request. And then I have a binding calling service bus. This is my queue. And I have the collector that's going to receive my message. So if you remove the logging lines here, in 3 lines of code, I'm receiving the message from a HTTP request, dropping that message into a queue, and then returning HTTP OK, right? So the programming model abstracts all this complexity for you, right? So it's very, very, very friendly. And the second function, the one that gets it from the queue and drops it into the document-based database, receives it from service bus, gets it from Cosmos, and drops it into Cosmos. And again, if you remove the logging lines, it's only 1 line of code. Reads from the queue and drops it into document-based database, right? So these are the big advantage of the programming model. So you just need to do that, and then everything else is taken care of you. Of course, I'm not doing any kind of validations or any kind of mappings that you will need to implement in your code. But what I'm trying to show you here is that the complexities of the endpoints are abstracted for you. You only care about the core code of your business, right? And I'm gonna run this one here. So I have, this is my Cosmos DB database, right? So if I explore here, I don't have any messages there. So I'm using here VS Code. So VS Code has an extension for sending HTTP requests. So I'm gonna send some requests. These are very sensitive, so very sensitive documents. I'm gonna send these documents to my function, right? So I'm triggering this URL here. I'm gonna send this request. And so I just received my response, and as you can see here, 6 seconds. Took very long, right? Because it was a cold start. If I hit it again, 200 milliseconds. See the difference? So because the next time there is already a warm instance. Yeah. So this is where the cold start can impact you. And if I go now to Cosmos DB, if I refresh, the demo gods are nice with me. I have the 2 documents here already, right? So these are the documents I just submitted. And I can even say, I'm gonna do this quickly to show you also the demo. So I can run it locally, right? I can debug it locally. And this is also one of the benefits of the tooling. So instead of sending it to the cloud, I'm gonna swap my base path to say local. I'm gonna send another document here. And this will trigger my function locally if everything goes well. Oh, it's running now. So forgot. So now it's loading my code into memory, so hopefully it doesn't take too long. A bit slow. So I'm trying to debug the code locally. Hopefully it's not too bad. So I have the runtime installed locally on my machine. So now I should be able to hit it from VS Code as well. So I'm going to send another request. This is going to go to my local computer, and I should trigger. I'm reaching the breakpoint. Yeah. So these are the benefits that you get with the tooling. So I can develop this locally and test it locally. Once I'm happy with the end result, then I can publish with my CI/CD pipeline. So I can let it run. This is the first function. I can let it run, and then there will be the other function will pick it up from the queue if there is another. So there are two competing consumers here. So there is one on the cloud and one locally. So probably the one on the cloud won. But if the one on the cloud was stopped, then I would receive that message locally from the queue, which is on the cloud. And I can show you quickly. So this is the tooling that you also get on Azure for serverless. So you can see the application map, meaning you see this is my instance, it's talking to Service Bus, it's talking to Cosmos DB, and I can see the latency between the two. So talking to Service Bus, this one was 1.8 seconds, that was very slow, and this one was 165 milliseconds. So I can see where the bottlenecks are. This is all out of the box. I just enable API sites, I enable logging, and that's it. Live metrics as well. I can see the live metrics. Actually, they were here already. So I can send some more to the cloud. I'm going to send some requests here. And then I should see some requests coming through. You see? So now I have some requests coming through. I can see these all on real time. You see? Plus, I can also see, I can search for my logs. I implemented some custom logging. I can say, search for the event 101. So I'm using event IDs on my logging. I found one event, which is when the event was received by the first function. And then after this, I can say, show me all the events that are related to this event, and show it to me in the timeline. So I can say where the bottlenecks are. Very powerful, and you get these kind of toolings in the different cloud providers. Okay, so the next demo is serverless request bin. How many of you have used request bin in your development? Not many people. So request bin is one tool that you can send HTTP requests, and you can inspect your calls. These are very handy if you're developing and you're calling a backend and you don't know how your client is behaving. So you can send your request to the backend. So I created this serverless HTTP request bin. So at the moment, I don't have anything here. So if I send some requests from VS Code.
It's similar to Postman.
Similar to Postman, yeah. But this is very similar to Postman or curl, yeah. So I'm sending some requests to my request bin. Now I can inspect those requests from here. Yeah, so I can see I received these requests with the get method. These were my query params. These were my headers and all that, right? So this is a tool that a lot of developers tend to use, but the problem is if you're using a cloud-based serverless, the ones that are for free, the problem is that sometimes you're sending confidential information. I've seen so many devs that they send JW tokens, right, with all your token, right? And if they are logging that or someone else gets your request bin, then they can see those tokens, right? But in this case, this is my own request bin, and I have it here. So I have full control of this. So I know that no one else is taking a look at my requests. I'm going to show you quickly, just very quickly. So the code of this one, I don't have time, but I want to show you. So the source code of the serverless request bin is on my GitHub. And even if you want to deploy it to Azure, you just click this button. It will take you to this page, and you just select your resource group, you give it a name, and then you deploy, and that's it. You have your serverless request being pretty much for free. The only thing you need to pay for is storage, which is very cheap because you get million requests per month for free, and App Insights, which is all you can also get the free. So the monitoring tool, you can get the free instance. You deploy it, and that's it. You already have your serverless request being. So I'm planning to add some documentation to this repo later, and yeah, so it will be available for you to play around if you want it. Cool. So key takeaways. So as I mentioned, one of the main advantage of serverless is productivity. We saw there are programming models in less than 10 lines of code. I was able to read from a HTTP request, get the message, put it into a queue, get it from the queue, and drop it into a database, right? So very, very productive. And not only for that, but also you saw the tooling. So you get all the monitoring for pretty much for free. I mean, you just enable it, and that's it. You get all these advantages. It's ideal for bursty loads, but you need to think that each instance has to be short-lived, so it cannot run for more than 10 minutes. There are some specific use cases. There are some cases where you shouldn't be using serverless, and as we saw, you can trigger serverless APIs not only with HTTP requests, but also with all types of events. We can say that these are enterprise grade, but only for certain scenarios, right? So integration pops up, enterprise grade, very secure and all that. If you want a very, very low latency API for your web app, probably not enterprise grade for that use case. It's evolving very rapidly, still maturing, so we cannot say that serverless is mature yet. And you need to know the capabilities of your own cloud provider. So we saw the demo, it was Azure, AWS Lambda would have different capabilities, in GCP the same. Cool. So we would have time probably for 1 or 2 questions. Yep.
Hi, so you mentioned that the mitigation around the cold start might be that you can keep it warm.
Yeah.
So are you finding that the providers of serverless platforms have service level agreements? I mean, are they saying to you as a developer, it stays in the cache for X number of seconds or whatever. Otherwise, that could all change according to their price sensitivity. They might say, look, we don't want to let you sit around for 10 seconds doing nothing.
They tell you for how long they keep it. However, they don't guarantee you that they will keep it forever. So they can recycle your instance at any time. And that's the same with VMs and Faas, right? They can recycle your VM. So in my serverless request bin, everything is persistent into a memory cache. So if this was, because it's only for my dev, it's okay, because if I lose it, I can just resend. But you wouldn't do that for your production data, right? But yeah, and even if you keep pinging it, as I said, you can keep it warm. They can recycle at any time. I forgot to mention, so my strategy to keep my instance warm here. So I have this function. So this function runs every 5 minutes. And the only sole purpose of this function is to keep my instance running every time. And even with that, I can see after 4 hours, they would recycle my instance. And I have no control over that. Cool. Yeah, good question. Another question, the last one? Yep.
So there's a kind of an opinion that with IaaS, that it's wonderful for development, but when time comes for production, there is a case to be bringing, may well be to the private cloud, right? But for servers, particularly based on what you said during the talk and also what you showed, is it the reverse? Like once you development you do wherever, maybe IaaS or wherever, but in production, when you know the parameters behavior very well, then you put it into servers, given the no charges when it's not running.
So I think, as I mentioned, that serverless has benefits for devs and ops, right? So on IaaS, the benefits for ops are very minimum, right? So ops still need to patch the VM and the operating system and all that. With serverless, they don't have that. So you get the benefits for not only for the devs that we saw, but also for the ops. They can see what's happening. They have all the logs out of the box, and it's very affordable as well.
Yeah, but what I'm trying to say is in the devs, like instance disappears, just like what you said during the talk while you're developing. That's not a good scenario.
Oh no, while you're developing, everything is local, right? And if there isn't, so the best practice, there is one slide that I'm running out of time, but there is one slide that I couldn't include because of the time. There are some best practices. Your serverless functions should be stateless. There are other patterns that allow you to be stateful, but everything has to be stateless. So if the instance is rebooted in the middle of that, then it should be fine because you can just create a new instance in that. So yeah, it has to be. So one of the limitations is that they have to be stateless. Sorry. Cool. Thank you so much. Great to see you here.